All right, so this section is 6.1, and it's about exponentials and logarithms. And this is kind of an intro. So I believe the rest of this section will be about exponentials and logarithms kind of from here on out. If you're wondering what in the world we're even talking about, these are what we call inverses of each other. So we just got done talking about inverse functions. And so exponentials, you've probably heard of those before, but the inverse of an exponential, how you undo or solve an exponential, is by using what we call a logarithm. All right, so we're going to start this conversation talking about exponential functions. And this is just from the paper on the backside, so just ignore that, all right? That's like nothing. And so you have two types of exponential functions. You have exponential growth and decay, and what's happening here is that this function, as your x's get bigger, the y values are getting bigger, so that's why we call it a growth function. For this one, as your x's are getting bigger, your y values are actually getting smaller, so we call it a decay function. Both functions are written in the form a times b to the x, and what makes it an exponential is that you have something to the power of x. And so exponential, I always say there's an x in the exponent. That's what makes it exponential. And so if it's growth, what's being raised to the power of x is going to be greater than 1. So this could be like 2 to the x or 3 to the x, or even a decimal 2.5 to the x, as long as that base, which is why we label it b, as long as that base is bigger than 1, then this is going to grow. It doesn't matter if there's anything being multiplied in the front or added or subtracted from the end. If that base is bigger than 1, it's a growth. If the base is between 0 and 1, so you're going to see maybe some decimals or some fractions, so like 1/2 to the power of x, or 1/3 to the power of x, or you could even say like 3/4 to the power of x. As long as that number is between 0 and 1, it is a decay function. And so that's why this is going to, as you get bigger x's, you're going to have smaller y values. So a couple things to note. None of the b's will ever be negative. So you'll never have like -2 to a power of x. This is not an exponential. What's actually happening here, as you raise it to the power of x, your function is alternating between positives and negatives. Because if you do -2 to the first, you'll have a negative number. But if you do -2 to the second, you would have a positive number. And so it would jump back and forth between positives and negatives, which is not going to make an exponential. Also, we don't have 1 to the power of x, because 1 to any power is always equal to 1, right? That one's always 1. So that would just be a horizontal line, which would be super boring and would not represent a growth or decay. So these are two situations that you won't ever see when talking about an exponential. You would either see greater than 1 or between 0 and 1. All right, so what we're going to do is we are going to graph some functions, and we're going to talk about the transformations of those functions and what those look like, all right? So the first one we're going to graph x 2 to the x minus 1. And so before we graph 2 to the x minus 1, we actually want to take a look at 2 to the x. And so what we're going to do is we're going to make a table of what 2 to the x would look like. And so as you're making this table, you want to pick x values very intentionally here, all right? So when you pick your x's, it's all about picking smart x's. And so a really good place to start for just the basic 2 to the x function is to start when x is 0. What happens when you have a power of 0? Well, anything to the 0 power is equal to 1. And that is always true, whether it's a fraction or a whole number or anything crazy like that. If you have something to the power of 0, it is always equal to 1. Moving in the positive direction, if you plug in 1, 2 to the power of 1 is equal to 2. Anything to the first power is equal to itself. And so that's why we start off with those two. And then you're going to put another point on this way so you can see this growth happening. So this would be 2 to the power of 2, and 2 squared is 4. If you wanted to put another one on here, you could, right? 3. So 2 to the power of 3, that would be 2 times 2 times 2, so that would be 8. So 2 cubed is 8. And so what we would see right now is we would see this portion of the graph. And what we also want to see is this portion as well. So we want to see what's happening both in the negatives and in the positives. And so this gets a little bit trickier when you start plugging in negative exponents. So this would be, sorry, I don't need to print this either. This would be 2 to the power of negative 1. And what's going to happen, there's kind of two ways to think about it. This one, you could just throw it in your calculator, get a value, right? Two, what's going to happen with this negative exponent is it's going to turn this into a fraction. And that 2 is going to be to the power of 1, but it's now going to be in the denominator. And so it'd be 1 over 2. And so 2 to the negative first power is just 1/2. Continuing in this direction, if you looked at 2 to the negative second, we would have, because of the negative, it would turn into a fraction. And in the denominator of that fraction would be 2 to the power of 2. It's not negative anymore because it's going to go in the denominator. So 2 to the power of 2 is 4. So that would be 1/4. And so what we can see is that we would have 2, negative 2, 1/4, 1/2, 1, and 2, 4, and then 3, 8. And so we would have a graph that looks like this. All right, so for this question, now that we know what the graph of 2x looks like, it wants us to graph 2x minus 1. And so that minus 1 is not with the x, it's outside, so it's affecting the y's. So what's going to happen here is all the y values are just going to move down 1. And so you can either take all your y values here and subtract 1 from them, or you can just move each of these y values down 1, just like this. By the way, these values would be just close to the negative 1. So that's going to have the same shape there, but just shift down 1. So it would look like that. All right, next question deals with the graph of negative 2 to the x. This negative is not being raised to the power of x. It's just a negative in the front, which technically means a negative 1 in the front. So if you start with your original graph, original table, and we go through the same values that we did before. So this was 1/4, 1/2, 1, 2, and 4. Then what does that negative do in terms of transformations? Well, that negative is affecting the y value because it's not in with the x. Remember, anything that affects the x would be directly next to the x. And what's going to happen here is it's going to take all the y values and it's going to change them, change their signs. So they're going to go from positive to negative or negative to positive, vice versa. And so all of these will become negatives. And what's going to happen is instead of your graph being this direction, it will flip over. It does not change it from growth or decay. It is still considered a growth, but there is a reflection happening here. All right, so plotting these, we would have negative 2, negative 1/4, negative 1, negative 1/2, 0, negative 1, 1, negative 2, and 2, negative 4. And it would look like that. So as long as you can make the table of the base function, then you are free to do the transformations, just like we talked about earlier this year with the transformations unit. All right, so we have some more problems, some more graphs to make. So this next one, I know you can probably barely see it because of the hole punch. This is 1/3 to the power of x, and they want us to graph 1/3 to the power of x minus 1. So if we're going to make our original table, you're still going to do 0, 1, 2, and then negative 1, negative 2. Those are some great places to start to see what's happening here. And so when you plug in these values, we have to figure out what the 1/3 to the power is. Well, I'm going to start with 0 because that's the easiest. 1/3 to the power of 0. Anything to the 0 power is equal to 1. Plug in 1, it would be 1/3 to the power of 1, and anything to the power of 1 is itself, so that would be 1/3. And then this one here I'm going to write out. This would be 1/3 squared, which is technically 1/3 times 1/3, and 1/3 times 1/3 is 1/9. You could think about it as squaring the top and squaring the bottom as well. So it'd be 1 squared on top and then 3 squared on the bottom. All right, heading this direction, we have 1/3 to the negative first. And what's going to happen here when you raise a fraction to the negative exponent, instead of it becoming a fraction, it's actually going to turn back into an integer. So 1/3 to the negative first is actually going to just be equal to 3. So that 3 in the denominator essentially is going to come back up to the numerator and just have the 3. And since it's to the -1, it's just 3 to the power of 1, which is just 3. Same thing is going to happen on this when you have 1/3 to the negative second. That -2 is going to, the negative is going to turn it into a whole integer. And the 2 means that you have to square it. So it's going to be 3 squared, and 3 squared is equal to 9. And so essentially what happened was the powers that were here before, right, power of 1, power of 2, became the negatives. And so you're kind of seeing the same pattern where you have whole numbers and then it gets into these fractions, just in reverse, because this is a decay problem versus a growth problem. So -2, 9, -1, 3, 0, 1, 1 1/3, and then 2 1/9. And you're going to have a graph that looks just like this. By the way, it's going to hug the x-axis as it goes out. It's not going to drop below. And technically, there is an asymptote here. So this graph will get closer and closer and closer to 0. So as you go this direction, these numbers are going to get closer to 0. They won't ever get to 0, and they won't ever get to the negatives. Now, the graph that they wanted us to graph is 1/3 to the x minus 1. And so that -1 is in with the x. It's in the exponent with the x. And so that's going to move it either to the left or the right. And so you have to remember, because of the -1, we want to say it goes to the left because -1, but technically everything with x is backwards. So this moves it to the right 1. And so what you're going to do is you're going to shift all these points right 1. And so you can either do that on the graph, or you could do that in the table. You would take all these points and just add 1 to them, and that would end up with this new graph. And so that would be the graph of 1/3 x to the, or 1/3 to the x minus 1.
Pardon the interruption.
Oops, sorry, hold on. All right, so if you want to go ahead and hit pause, the next few problems are going to be very similar. So see what you can come up with. Just know that this one has a couple transformations, right? So you're going to start with 3 to the x, see if you can make the table, and then see if you can do the appropriate transformations. I would recommend when you make the table that you make a new table with your transformations and just graph that. So try the next 3. Am I right? 3? Try the next 3 and see how they go. So hit pause, give them a shot, see what you come up with. And then I'll throw the solutions up. So don't hit play until you're ready to look at the next 3. All right, so here's what you should have for that first one. So you should start with x and 3 to the x. So I just picked the normal x's that we've picked for all of them. Here's what you should have for 3 to the x. We talked about how to find these numbers in other problems. So hopefully those went all right. If not, let me know. And then the transformations for this problem, in with the x is a negative, so it's going to change all the signs of x from either positive to negative or vice versa. So you see that here, all of your x's have changed. And then the 2 is not with the x, it's outside of the exponent, so it's not with the x, so it's affecting the y values. So all those y's you're going to add 2. So I took all these numbers and I added 2. And by the way, on the fractions, you don't have to get super fancy. This is 2 1/9, and that's okay in order to take a look at the graph here. That's much easier, 2 1/9, than saying 19/9 or something like that. So it's okay to leave these as mixed numbers here so that you can see the graph. And so here's what it looks like. So the asymptote that used to be at 0 for this problem has moved up, and it is now at +2 because of the +2. Everything has moved up. It is a growth problem, but because of the negative x, it's going to kind of appear as a decay, but technically that's a growth value there with a transformation. Feel free to hit pause, take some notes, let me know if you have any questions about that. So here's the next one. So you should have started with 6 to the power of x, and you just pick your standard x values. And then here's what you get after you raise them to those powers. In terms of the transformations here, we see the negative in the front. That's not with the x, and so that negative is affecting the y's. So all your y values are going to change sign. So that's why I have negative y here. And if you notice, all the y values are now negatives. Also, we have x minus 3, and so because it's in the exponent with the x, it's going to affect the x values. And because it says minus 3, and we know everything with x is backwards, you're actually going to add 3. So all of those x values, we added 3 to them. And then I plotted them, and I just kind of noticed that at 5, it's like super far down there, right? I missed one at 4, -6. Whoops. So I guess I could get a little bit more accurate there, but one of them was off the grid, and that's okay, but you can kind of see the curve here. And the asymptote that was at 0 is still at 0 because this function didn't move up or down at all. It just flipped over. Once again, hit pause if you need to take a look at those values, check and see. Let me know if you have any questions on them. And then here was the last one. We have done the 1/2 power, or x to the, sorry, 1/2 to the power of x, right? Did we do that one? Nope, we didn't. So this was a new table for you that you could have made there. And then based off the transformations, they're actually almost the same as the last problem. There was a negative in the very front, which is affecting the y's. So all those y's change from positive to negative. And then the x said x plus 1, and the 1 was in the exponent with the x, so it affects the x. But everything with x is backwards, so instead of adding 1, we subtract 1. So all of those x's, I took 1 away, and then that ended up with our exponential there. So once again, hit pause. If you need to check any numbers, let me know what questions you have. I am here to help on those. All right, so here's the next question. We have the graph, and they want us to write the equation in the form a to the power of x plus k equals y. And so what we need to do is we have to figure out two values here. We have to figure out the a value, and we have to figure out the k value. The easiest one to figure out is actually the k, and that's because this graph has shifted off of the x-axis. If you remember on a normal exponential that we've seen, it comes down and it runs along the x-axis. Well, this one no longer does that. It has shifted up to positive 2, which means that k is 2. If this was running along 3, then k would be 3. If it had moved down to like -4, then k would be -4. And so that k value is how far up or down this has shifted, so where this is running now. In terms of finding a, it's a little bit more complicated. So I'm going to write what we have so far. So we know y equals a to the x plus 2. And in order to find the a value, you have to pick a point on your graph to plug in for x and y. And when you plug it in for x and y, you can solve for a. Now, don't just pick any random point. You want to pick a nice point, one that's really obvious that you know of. So for example, look at that one right there. That one is the coordinate point 0, 3. And so let's see if we use 0, 3, what's going to happen. So this would be 3 equals a to the 0 plus 2. A to the 0 is always 1, right? No matter what a is, like anything to the 0 power is 1. So that's not really that great of a point to pick because that doesn't really tell us anything about a. It could be 8, it could be 20, it could be negative. We don't really know because anything to the 0 power is 1. So that's not super helpful. So we need a different point. So this point wasn't useful. I see one right here. That's a nice point. That's at -1, 6. So I'm going to try this new point, plug it in for x and y, and see what happens there. So now we have 6 equals a to the -1st plus 2. So you can solve this by subtracting 2. So 4 equals a to the -1st power. And then you might not know the algebra associated with this. What you can actually do is you can, if you have a power of -1, if you raise this to a power of -1, you would multiply those together and get +1, which would leave you with just an a. And so this would be 4 to the -1 power. And we talked about earlier when we were figuring out what powers to negatives were, that means that that's actually a fraction, and it's 1 over 4. So your a value is a fourth. So your actual formula would be y equals 1/4 x plus 2. That would give you the equation of that exponential there. So finding the k value was pretty easy if you knew what you were looking for, and finding the a value is a little bit harder once you get into this part, all right? Let me know as you're working through Map of Math or as you're taking these notes if you have any questions here on what happened, and we can go over those. All right, so that's it in terms of talking about the graphs of exponentials. And so what we're going to do now is we're going to transition to the inverses of exponentials, and we're going to talk about the logarithm. And so this is kind of an important idea that exponentials and logarithms, they are what we call inverses of each other. And because they're inverses, technically you could switch x and y and then solve for y, and you could get the inverse form, right? And so that's what you see here is when you actually do the inverse and you work through the operations, what's going to happen is this exponential can turn into what we call a logarithm by making a few adjustments. And so sometimes some equations that we'll have will be easier to work with as exponentials. Sometimes they'll be easier to work with as logarithms. And we're just going to be jumping back and forth between them, okay? And so this is just the process of converting. So if you have an exponential y equals some base to the power of x, then you can convert and put the x equals, instead of y equals, it becomes x equals log with that same base. So whatever your base was here, that'll be the same base of the log of y. And these two are equivalent statements. And so they're essentially what we call equal statements. So if you can solve in this form, you can convert it and solve it in this one, or vice versa. So what we're going to do on this this next slide essentially is we're just going to practice converting back and forth. So there's not really any solving here, just convert away, okay? So if you have 2 cubed equals 8, that is a true statement, right? 2 cubed is equal to 8. Let me get a better view of that. And so if we want to convert this to a logarithm, put it in logarithmic form, we would say that 3 is equal to log base 2 of 8. So if you were to type in a calculator log base 2 of 8, you would get that that is equal to 3. And so that comes from this conversion of an exponential. So let's take a look at the next one. 5 to the negative third is 1 over 125. And this is true because this would be 5 cubed, right? 5 cubed is 125. And then because it's a negative, it goes at the bottom of a fraction. So in logarithmic form, we can say negative 3 equals log base 5 of 1 over 125. And so if you were to type this into a calculator, it would say that it's equal to negative 3. All right, same thing for this last one here. 4 to the 5 halves. 5 halves means you raise it to the power of 5 and then take the square root. That's what a fractional exponent means, is that's a root. Or you could take the square root and raise it to the power of 5. So, for example, the square root of 4 is 2, and 2 to the power of 5 is equal to 32. So this is, once again, a true statement. In logarithmic form, it would be 5 halves equals log base 4 of 32. So if you were to type in log base 4 of 32, you would get in your calculator that that's equal to 5 halves. All right. I'm going to let you pause and work through the rest of them. So hit pause for me, and then I'm going to just show you the solutions there so you can see how you did on the converting. So pause, convert. All right, so here are the solutions to those. So if you need to pause right now so you can take a look at all of them, that's fine. These should all be, it's just the same thing, right? If the base is a third, the base of the log, and we do call it the log base. the bases are the same. And essentially what's happening is what it's equal to is switching with the exponent. And so you have a switch happening there. Same thing for these things, come straight from the equations there. The base is the same base. This one's kind of different. So the base of this one is E. So when you go to say log base E, log base E is actually something that's very common when you're doing math with like real world applications and things like that. And when you have base E, that's actually referred to as a natural logarithm. And so instead of writing log base E, which would happen a ton, you instead can write the natural log, ln, and we refer to it, you could either say natural log or ln, one of the two. So log base E or ln, if you had log base E, it would be 1 equals 0. But just know that that log base E is equivalent to a natural log. And then these other ones, you were converting the other direction. Hopefully you picked up on that to convert the other direction. It's the same thing. Whatever the base of the log was, raised to the power of what it was equal to, equals what you were taking the log of the number on the inside. And this should be a true statement when you're done. 5 squared is 25, right? And if you don't get a true statement at the end, then you put things in the wrong spots. Like it's not 2 to the 5th, it's 5 squared. It's not, 25 squared or anything like that. It's the true statement with those numbers. Same thing here, 25 to the 1/2 equals 5. Well, we mentioned earlier that a fractional exponent is a root, and so that's a square root. So that would be the square root of 25, which is 5. All right, same thing, check those last ones. Let me know what questions you have as you're looking through. All right, so here's a My Open Math type question that you would see. It says, write the equation in exponential form, assume all constants are positive and not equal to 1. Why do they say that? Because at the very beginning of this lesson, we said, hey, that base, right? It can't be 0 or it can't be 1 and it has to be positive. So that's why it says assume that they're positive and not equal to 1. So that all of those numbers would work in terms of the requirements for an exponential that we discussed at the very, very beginning. So if this is log base P of T equals C, the equation would be base P, because that's the base of your log, to the power of C equals T. Just convert. In this case, you don't have any any numbers, you only have variables. Next question right here says write the equation in logarithmic form. Once again, assume all constants are positive and not equal to 1 because of the same requirement for exponentials. So this would be log base, and your base of this equation is base 5. And then the C and the T are going to switch locations. So log base 5 of C equals T. All right, here's a few more. Log base 2 of 16 equals 4 can be written in the form 2 to the power of A equals B, and then it wants to know what A and B are. So what it's really saying is take this log, convert it, and A is the exponent and B is what it equals. So if you were just going to convert this, this would be 2 to the power of 4 equals 16. Just on the conversion like we've did on the last slide, the last page over here. And so A would be 4 and B would be 16. All right, next one is going the other direction. 4 to the power of 5 equals 1024 is equivalent to log base 4 of C equals D. And they want to know what C equals D is. And so you're just going to convert. Log base 4 of 1024 is going to be equal to 5. So C would be the 1024. And D would be 5. All right, so just a couple My Open Math equations, questions that you could see about the converting process there. All right, so up next, we're going to get into the graphs of some logarithms. And so we're also going to talk about the domain of these logarithms as well as some asymptotes. So just kind of quick refresher. If you remember, we said that exponentials and logarithms are inverses of each other, right? Inverses, which is why we cover inverses right before we talk about this section. And so here you see an exponential, And then here would be its inverse. It's a reflection about the line y equals x. We talked about this in the inverse section. So if you have absolutely know what I'm doing, I'm talking about, have you done the inverse section yet is my question. So it's a reflection there. And the main thing that you need to remember about this reflection is that your x's and your y's will switch. So your x's can become your y's, and your y's will become your new x's on your inverse. And so that's what we're going to use to help us graph these, is we're going to use the fact that this graph right here is formed because this graph, all the x and y values flip-flopped. They switched. All right, so we're going to graph log base 6 of x. And the base here is base 6. And so the original table that you're going to start with is the exponential x, or 6 to the power of x. Whatever that base is, that will be the base of your exponential. And so we're going to take a look at this exponential. And what we're going to do is we're going to turn it into the inverse table. And when we turn it into the inverse, that's what's going to get us the log base 6 of x. All right, so go back to its inverse, the exponential, because that's a much easier table to make. And then from there, we'll make the inverse, all right? So when you're making this exponential, we kind of stick to -2, -1, 0, 1, and 2. And then you're just plugging them in. Well, anything to the 0 power is 1. 6 to the first is 6. 6 squared is 36. And then here's where you get into the negatives. So 6 to the negative first, that's 1 over 6. And 6 to the negative second, that's 1 over 36, because that was 6 squared. And so starting with this table is much easier than trying to pick x values and plug them in there and figure out what's going on. Because all you have to do is you have to take this table and make the inverse of it. And the inverse is simply flip the x and the y's. So there's your x's, and here's your y's, and they have now become the x and the y of the new function, and our new function is our inverse function. And so we're going to go ahead and plot this. It'll be 1 over 36, so just on this side of 0, right? -2. 1/6, -1, 0, 1. I'm sorry, 1, 0. I'm saying them backwards in my head. 6, 1. And then 36, 2, which would be like way, way, way off the grid, right? So it's going to look like this. And so if you remember before, and I can even show you, like if I turn this way, right? If you remember before, there was a horizontal asymptote. Well, that horizontal asymptote, when you go to the inverse, becomes a vertical asymptote. So there is a vertical asymptote here at x equals 0. So what's happening is that as these numbers go down this way, they're getting closer and closer and closer to 0, the y-axis, but they're never actually getting there. All right, and so domain and range. The domain is all about your x values. The range is all about your y values. We've talked about these before, just not with a logarithm. So the domain x values, if you notice, it doesn't go anywhere past the y-axis, right? Because there's a vertical asymptote here. There's nothing over here. And so what that means is you can't take the log of a negative number. So if you have any kind of log, any kind of base in here, if you have a negative number, that is bad news, because those don't exist. So they're pretty much starting here at 0. They're not actually equal to 0 because there's a vertical asymptote there at 0, but it's going to go from 0 to infinity. So your domain is parentheses 0 to infinity. The range is all the y values. That's top to bottom. Well, this is very obviously going down forever, right? So there's no stopping the bottom. It's just going to keep going. And then this is going to go up. As it's going out, it is going up. There's no asymptotes or anything over here either. And so that means that the range is -infinity to infinity. Which, by the way, this is the reverse of the domain and range for an exponential, because if your x's and y's flip, your domain and range is also flip. All right, so I'm going to pause, or you should pause, right? You should pause the video, and you should try to graph this next logarithm, all right? So this one right here, see if you can graph it. If you're looking at it and you're like, goodness gracious, I have no idea where to start, you should start with x and 1 over 6 to the power of x. You should start with the exponential that has the same base as the log. So start there and see what you can come up with. When you're ready, go ahead and hit play, and I will pull the solutions up for you. All right, so here's what I have for my 1 over 6 to the x. Here's the y values that I found. And then to make the inverse, you literally just flip-flop your x's and your y's. So if you can make this table, it's not very difficult to make the logarithm table. And then, so I plotted those. You can see those happening there. Once again, there is a vertical asymptote here at 0. There's nothing over here in the negatives. So the domain is 0 to infinity. The range, negative infinity to infinity. By the way, that will always be your range. And that's what your graph should look like. So hit pause if you need to, so you can take a look at the graph, at the tables. And if you have questions, let me know. All right, last but not least, the last slide of this intro to exponentials and logs is talking about the domain, but it's talking about it in terms of we don't have a graph to look at. And so this is y equals log. And by the way, if there's no base written, it's technically base 10. So no base written, it's base 10. And then of 6 plus 5x. And we said earlier, and I literally don't have to go that far, that based off of what we noticed on the graphs is you can't take the log of a negative number. So there's a domain restriction here because whatever's on the inside of this logarithm cannot be negative. So 6 plus 5x has to be a positive number. So it has to be greater than 0. It cannot equal 0. At 0 is where the asymptote is, and we'll talk about that right here. And so we're looking for where it is greater than 0. So we just have to solve this linear inequality. So subtract 6 from both sides, divide by 5. So x has to be greater than negative 6 over 5. So your domain would be from negative 6 over 5 to infinity, everything greater. And then infinity always gets a parenthesis, and negative 6 over 5 also gets a parenthesis because we're not including the negative 6 over 5 because there would be an asymptote there. So if you want to add on, the vertical asymptote is at x equals negative 6 over 5. So domain is where it's greater than 0. Vertical asymptote is where it would be equal to 0. All right, so last piece here, it says the equation has a vertical asymptote. Where is it at? Well, whatever is on the inside, the vertical asymptote is where it equals 0. So what number do you plug in for that to be equal to 0? You would plug in negative 5. So when x equals negative 5 for this problem, there is a vertical asymptote. And that's because normally the asymptote's at 0, but this has been shifted. X plus 5, that 5 is in the parentheses with the x, and so it's affecting the x, right? If you think about your transformations, which means it would go to the left 5. And so if it was originally at 0, left 5 moves it to negative 5. And so that's what you're seeing happening there. All right, that is it for this section. Let me know what questions you have as you're working through the homework, my open math, all that fun stuff.